The first section here is section 11.1, Introduction to Logic. We're going to learn a few terms today, mostly. So the first thing is that logic is based on what are called statements. So the definition of a statement is a declarative sentence that is either true or false. So there are, of course, two parts to this definition. First thing is a declarative sentence, and the second thing is it's either true or false. So the idea that a declarative sentence, that means it's not a question, and that means it's not an imperative, a command. It is a declarative sentence, and it's either true or false. So I'm going to write some examples of statements, and we should try to figure out, examples of things that might claim to be statements, and we should try to figure out what's going on here. Okay, so this one here, Washington was the first president of the United States. Okay, that is a declarative statement. It is declaring something, and that thing can either be true or false. Okay, so it is declarative, and it is true or false. So that is definitely a statement. George Washington is the first president of the United States. Okay, here's another statement. The Miami Heat won the NBA Finals in 2015. Okay. Is that making a declarative statement, or is it a question or a command? No, it's making a declarative statement. So it is declarative. Is it either true or false? Yes, it's true or false. Is it true? No, it's not true, Pat. Do you know who won in 20? The Warriors won that year? Okay. So that is a false statement, but it still is a statement. It just happens to be false. So even though it's false, that doesn't mean it is disqualified from being a statement. Okay. The number of atoms in the universe is 10 to the 75th power. Okay. That is a statement that is declaring something, and it is either true or false. Okay. Seems to me it's likely to be false. Yeah, it seems odd that it would be exactly 10 to the 75th power, right? But I don't know for sure. So this is an interesting example here. This is a statement that is either true or false, but which we cannot know whether it is true or false. Okay. And the fact is that these statements actually do exist, even in mathematics, that there are statements which are either true or false, but that we cannot discover whether they're true or false. This was discovered by a mathematician named Gödel in the first half of the 20th century, and was a real problem for a few years until people just decided to ignore it. But it really angered people, that there are statements that are either true or false, but that cannot be proven. And this would be an example of such a thing, I suppose. I mean, you really have to line all the atoms up to find out, right? Now, you might say the number of atoms in the universe is about 10 to the 75th, but then I'm not sure if that's really a statement, because you haven't defined what about means, so there's no way to tell whether it's true or false. Okay, here's another statement. If x is positive and x squared is equal to 9, then x is equal to 3. Okay, if x is positive and x squared is equal to 9, then x is equal to 3. Okay, so that is saying something. Even though it's conditioning on saying that if x is positive and if x squared is 9, then x is equal to 3. But it is making a statement, and the statement is either true or false, and in this case it is true. E. He is nice. That is making a statement. It is saying that he is nice. It's not a question. It's not a command. But there is no way to verify the truth or falsity of this statement because he is not specified. Okay? Unless we somehow know that all he's are nice, there's no way to verify the truth or falsity of this. Right? And we know for sure that not all he's are nice. Right? Math professors exist, for example. Male math professors exist, for example. So we cannot figure out what's going on here. Okay, here's another example. X plus 3 is equal to 2x. Bless you. Okay, this is saying something. This is saying that x plus 3 is 2x. But there's no way to know if it's true or false unless we specify a value for x. So this is similar to the previous one in saying that he is nice. Okay, so it is not a full logical statement. It does not count. And then G, is this fun? Okay, well, that's not even declarative. And if something is not staking any sort of claim, then there's no way to tell if it's true or false. Even if the answer to the question happens to be yes, that does not make the statement true or false. Right? The statement is not claiming any truth. It is merely asking for something. So it's not a declarative statement. So it does not count as a statement. Okay, it's not a declarative sentence, however. Okay. All right, so we break down all statements into two types. Compound statements, and those use phrases like and, or, not, if, then. When a statement uses those words, it's a compound statement. And the other type are simple statements. And these do not use the above words. So we're going to define simple statements as ones that don't use these words. So let's look for some compound statements in the ones we have here. Okay, D looks like a compound statement because we use if, and then. Right. So I think that's the only compound statement up here in this example. In these examples here. Okay. So we're going to talk about these logical words here. This and, the or, the not, the if, the then. So and or are called conjunctions. And is called a conjunction. This is and then the logical way we write that is a caret, pointing upwards like that. So a conjunction is and the symbol for it is that upturned caret. A disjunction, disjunctions are or. And the symbol we use for that is the upside down caret. And it's important to know that this in logic is considered an inclusive or, which is not usually how we use or in English. So if both things are true, then the or statement turns out to be true. Okay? If I said 3 is a prime number or it is odd, that's a true statement because it is both prime and odd. So we allow the or statements to be that's called inclusive or. So in logic, the building block in logic is always the inclusive or. But that's different from how we usually use words. Like I would say the number 3 is prime or odd. You would say that sentence seems odd in English. But in logic, that sentence that's true. But in English, that would not be a sentence you would probably say. So there's a slight difference there in how the word or is used. And a negation is another kind of compound statement. This means not. And the symbol for that is this squiggly line or this there. The book uses that squiggly line. And I'm going to try to use that squiggly line, but I'm more used to using that little, I don't know what to call that, a little right angle or something like that points downward. And so I might mistakenly put that instead of the squiggly line as we go through. Okay, so I'm going to write down 2 simple statements, and then we're going to write down what the conjunctions of those various simple statements are. So we're just going to do an example with these conjunctions, disjunctions, and negations. So the statement P is going to be Ina likes popcorn. Q is going to be Fred likes peanuts. So then P and Q is now a compound statement of both of those 2 statements. And the compound statement is Ina likes popcorn and Fred likes peanuts. Okay, now we're going to do P or Q. This is now the phrase Ina likes popcorn or Fred likes peanuts or both. I'm adding that or both to make sure we remember that this is an inclusive or. It's allowed that both of them like the thing that they are claimed to like, even though the word or is in there. The statement not P and Q. Okay, this is a statement asserting the opposite of P and at the same time Q. So this statement is Ina does not like popcorn and Fred likes peanuts. So that is that statement there. We'll do another example with these simple conjunction, negations, and disjunctions before we talk about the implication. A new statement, P is going to be Fred likes Cindy. And Q is going to be Cindy likes Fred. Okay, so these are 2 statements. So how would we write that Cindy and Fred like each other? That would be P and Q. Fred likes Cindy and Cindy likes Fred. So that would be Fred and Cindy like each other. Okay, how would we say Fred likes Cindy, but Cindy does not like Fred? Well, we have Fred likes Cindy, but we don't have Cindy liking Fred. So that would be P and not Q. Okay, Fred and Cindy dislike each other. That's not P and not Q. Fred and Cindy dislike each other. Okay. And then the disjunction here is kind of odd. This would be Fred likes Cindy, or Cindy likes Fred, or they like each other, or both. Okay, logically that or both is there, but when we would, if you said a statement like Fred likes Cindy or Cindy likes Fred, you don't usually assume that they both like each other as a possible outcome, just by the way that we usually use or as an exclusive or, not an inclusive or. So if you want to be very sure, you kind of, you mention or both could possibly happen. Okay, so now for the implication. So this is a statement of the form if ... then ... And the way we write it is an arrow like this or a double arrow. The book has the single arrow. The double arrow I think is more common, and so I might mistakenly write it. I'm going to try to write the single arrow though. Okay. So an example of an implication, if P is equal to a number is even and Q is equal to a number is divisible by 2, then P implies Q is the statement if a number is even, then it is divisible by 2. So that is an implication, an example of an implication. I'm going to try to think of another slightly complicated one. P is it is raining. Q is the grass is wet. Okay. P implies Q is saying if it is raining, then the grass is wet. Right, this is another true statement. That's obvious. But that's different from saying if the grass is wet, then it is raining. Because that's maybe not true, right? It's certain that if it is raining, the grass is wet. But if the grass is wet, it may not be raining. The grass might still be wet from a previous rain. Or the grass might be wet with morning dew. Right? Doesn't necessarily mean that if the grass is wet, then it's raining. So implications only go in one direction. Okay, the homework for today, which is due Friday, is 2, 4, 6, 12, 18, 20, 24, and 26. And the book is up here if you need that.